Great. So yeah, this is machine learning, and obviously there are lots of machine learning frameworks that are implemented in OpenCL, SYCL, and all those sorts of things. We've got some experts here who have presented and interested in machine learning, so I'll get them to introduce themselves first. We'll perhaps go right to left and say, yeah, name, institution, and kind of your machine learning background.
Well, as I told you in my last presentation, I'm Assad Breyer from University of Stuttgart, and we are currently implementing a least squares support vector machine as machine learning application for binary classification currently. We plan to further improve it performance-wise and feature-wise, for example, to also support multi-class classification, for example.
Hello, Chris Gehring from Mobileye. I'm really quite, I guess, new and old to this whole machine learning thing, but my interest, and someone said it earlier, is to try, I mean, Mobileye is taking this mainstream, right? Millions of cars running this code, is to how to take what we're doing here, which is very interesting, and make it accessible to general developers, the sorts of people that we have at Mobileye where we want them to develop algorithms, not to become experts in SYCL or the framework. So that's kind of where my focus is.
Hi, Dylan Angus from Codeplay. I've worked on different DNN frameworks like SYCL DNN and 1DNN. I've also worked on different model loading frameworks like Onyx Runtime and Glow. And so most of my work has been around that and focused on that.
So you guys know me. Machine learning is, so I've been involved in machine learning for the last 6 years since I've been involved in autonomous vehicles. Lately, I've been, mostly been involved in it from, other than the SYCL part that I talked about in my talk, that we do a lot of work with trying to put SYCL into machine learning. I've also been involved with the standardization of machine learning in SC42 at ISO, and as well as SC38, which is involving with autonomous vehicle safety. And right now, the big work that they're doing is how to make machine learning safe. And one of the paper that is the lead paper on that comes from University of Waterloo, which is my alma mater. And we've been looking very carefully about this big question, which is obviously emerging now, especially with ChatGPT, how to make machine learning safe.
That's great. So I'll start off with the first question, but I really want questions from you guys. So have a think about what you'd like to ask this panel. But the first question to kind of get warmed up is that most people, when they want to use AI or write a program that uses AI, they don't really write OpenCL or SYCL. They use the kind of big Duplo or Lego building blocks to kind of plug these massive things together in PyTorch or TensorFlow. So what role does OpenCL and SYCL and other programming models have in that ecosystem? Who is the target audience for these programming models?
I think the target audience is mostly the implementers and maintainers, for example, for PyTorch or TensorFlow, because most the new, for example, ChatGPT needs to run or to train on supercomputers with different hardware. Then we have it on the edge with completely different hardware on normal workstations, on laptops with integrated GPUs, with AMD GPUs, Intel GPUs, and with other hardware like FPGAs or even more specialized processors. So if the implementer do not use something like OpenCL or SYCL, they have to use some vendor-specific programming framework and implement their code like 12, 10, 20 times on different hardware platforms, which is a quite mess. If you, for example, want to add new features, you have to implement it in 20 different places, or if you find a bug, you have to fix it in 20 different places. And if you use something like SYCL or OpenCL, which can run all hardware platforms, you have your code essentially once, and if you find a bug or if you want to implement a new feature as a maintainer, you have to look only at one place in your code. So it's more for the implementers and maintainers, I think.
I mean, I would agree with that. I mean, what we've seen at Mobileye running on the accelerators is, until now, practically assembler. I mean, hand tweaking these things into life. Nothing unreadable, most of the effort, it's so difficult to develop kernels because they're just so tricky. So we're pushing, and this is our involvement in this, into OpenCL. But even in OpenCL, it still becomes, you still end up with quite unreadable, you know, it's not, it doesn't give you an abstraction into what they're really dealing with. So I think one of the things we're working on is, you know, to get people to think of if they're working in tensors, they should be thinking of tensors, not bits and bytes and OpenCL, and always trying to push it up, always trying to abstract it to the right level. I think SYCL, it's interesting that SYCL probably provides a better platform for that, and there aren't many OpenCL, they'll hate me for saying that. I think that SYCL may be going to provide us with a better platform, but just pushing it up so that they're thinking about, they've got to be thinking about the problem, not the implementation, and that's actually always what it's about, and that's what makes it mainstream, that you don't. And then if you have solutions that solve the problem, then you can move them around, right? But it's always, I'm not sure that answers the question. I mean, seriously, who cares whether it's SYCL or OpenCL or what's below? It's about solving the problem without getting so far above. And I think probably what happens with PyTorch and that because you still need to be able to optimize it, right? Especially in anything, either for HPC, where, you know, you need a lot of bang, or in what we're doing, which is autonomous driving, where you need efficiency. I mean, you need a lot of bang, but you need very little power, right? So you've got to get it to the level where it's abstract enough, but still optimizable enough, as it were. Otherwise, it becomes too vague by the time it gets to the hardware.
I think there's something to be said about working with like safety critical systems, like what Michael was speaking about. And I think there'll be a bigger push to more open source frameworks like SYCL and OpenCL implementations, where users and vendors are more likely to move toward these things as opposed to proprietary information, proprietary libraries, because they can actually see the implementation, actually adjust it, and know what it's actually adhering to, and put it through actual regulations and systems that you can't really get with these proprietary systems.
I really like these answers. The optimization, the safety, yeah. So the thing that we now know, of course, is that with DNNs and ML models and things like that, the strength in these lies in the hierarchical structure, which is basically composed of a bunch of parametric, sequence of parametric, which is convolutions, and non-parametric things like rectified linear layers. And these things are essentially notoriously are computationally very expensive. And they generate large amounts of highly parallelizable work. And so for that reason, we turn to GPU languages. OpenCL, SYCL is higher than OpenCL. So maybe, therefore, it's easier to tile and optimize. Maybe, even I'm a big believer in SYCL. I can certainly see that. Even that's sometimes probably not enough, because GPU still remains incredibly challenging to optimize for locality and parallelism. We know that. And that's why, you know, that we're turning toward things like tensor cores from NVIDIA, microarchitectures from AMD to solve that problem. And they're, you know, in the world of machine learning systems, we're turning toward things like MLIR, scheduling frameworks like TVM, more recently Triton with polyhedral compilations to try to solve the problem, which is fundamentally trying to recreate these microkernels that are very, very optimized at the cuDNNs, cuBLAS, and the tensor RT level at a higher level. And if you know, to Tom's question, right now, SYCL and OpenCL and language like that, and I wish Neil were here. This would be a great opportunity to say, this is where it supports these frameworks. But the question remains, are they going to be enough to be able to generate these extremely efficient hand-coded kernel? And that's the big question right now. We don't know if they can. Triton AI may be able to do that. And Triton AI is supposed to be used in ChatGPT by OpenAI, whatever. But we don't know, we don't know for sure. I mean, SYCL is capable of a tremendous amount of tiling. And Triton AI is basically a tiling language. We know that the computation efficiencies of OpenCL and SYCL is still like all over the place in the work group, right? When they walk, it's still walking all over the place. What you want to do is do a scheduling that allows you to put everything together into a tile. Okay, sorry. I'm gonna yield my time.
there's an interesting thing there, which is, I think is often a problem, which is in a commercial environment is you can over-focus on the efficiency at the beginning. And I wrote a slide a couple of years ago which said, hate to say this in front of academics because I'll get, but basically efficiency is the amount of effort to do useful work or something, right? Which means you first have to get it working and then you make it efficient. And I think one thing that we see is in our environment, which is, going at 1,000,000 miles an hour, that you can fall behind if you focus too much on the efficiency, which, you've eventually got to get there, but you've got to have something working. You can be as efficient as you want, but if it doesn't work, you're not in the market. So that's, I think, get it working and then make it efficient. You can't do, actually, by definition, you can't make it efficient and then get it working, right? And I think there's sometimes, it's interesting looking at this, focusing on the minute details, but actually we've got to get the big picture working first and then make it work.
And incidentally, my answer is provided by ChatGPT.
He's the fifth person.
Yeah, the fifth member of our panel. Yeah, any questions from the people in the room they'd like to ask our panelists? Yep. Let's wait for the microphone.
So NVIDIA is kind of leading the market in terms of bringing in new features that can be used for, say, AI applications. How can SYCL integrate these new features, these new hardware, say cores or different types of memory, and can we keep up? Can SYCL be used in as up-to-date a manner as CUDA?
I think SYCL should implement such features. However, maybe like extensions in OpenCL that, for example, the CUDA Tensor cores can boost performance dramatically on NVIDIA GPUs, but many hardware platforms do not support something like Tensor cores. So if SYCL should stay in a way that it should work on every hardware platform, you cannot support Tensor cores. So you have to use some mechanism to be able to implement extensions that are standardized. So no vendor-like extensions, but standardized extensions that, for example, CUDA or other implementers can decide, okay, we want to implement a SYCL extension on this API interface that supports NVIDIA Tensor cores or AMD matrix units or Intel matrix engines in a way that it's performant for their application.
So I'll add to that. FPGA. That's right. The computational efficiency on GPUs actually is quite bad for machine learning, for most machine learning. It's like you're probably like using 20 or 30% of the die. FPGAs, computationally for AI, you can almost make it use 90% or maybe, I don't know if 100% is ever possible. But SYCL and FPGA, that's another way that we can do it. But I also agree with Marcel, we've got to make sure that the ecosystem supports the wide range of things that NVIDIA has. NVIDIA has done an amazing job at proliferating this into every corner of the ecosystem. We don't necessarily have enough manpower, but we do if we have enough people that can do all of these things. But remember FPGA. FPGAs can do much greater computational density for AI workloads than GPUs. GPUs were not really designed. They were just conveniently on hand for AI.
It's funny, we don't use, we're probably in the FPGA camp. We're not running FPGAs in that we have much weaker, incredibly, I'll use the word incredibly, they're our product, incredibly efficient accelerators aimed at very specific tasks. I wasn't quite sure your question. I think one thing that CUDA probably has, and I'm really speaking, I'm guessing here, if I'm honest, don't know if they're allowed to, is that it is standard. And I think one problem that I see in the OpenCL is, and I know it's a problem, is in the extensions which aren't mandatory. Because then you start to slip towards the doesn't run everywhere. The idea is it runs everywhere, and as soon as you say, well, this is optional, then in a way you lose the advantage that you know where it will run. In fact, you don't know whether it will run into a runtime. So I'm not sure whether that's part of your question or not. if it's a standard, it has to do the whole standard. You can't implement something and say, well, it's optional, because then it's just a lucky dip.
Yeah, yeah. I'm not suggesting that, say, these new, tensor cores, which are exposed at the moment as an extension to DPC++, I'm not proposing that enters, say, the SYCL standard, because this is hard to, implement on various hardwares. But still, even as an extension, it's taken a long time for that to be implemented. And it's definitely a few years after, say, tensor cores have been normalized in use in CUDA code. And now there are newer features, and even adding these as extensions within different implementations takes a long time. And if users want to make use of these things, you simply cannot use the SYCL API really, unless you want to wait a few years.
Yeah, I think that's about dedicating resources to this. So stuff like dedicating resources to researching the API and seeing what we can and can't support. And I think what Michael was saying in his talk this morning, that there should probably be a specific TSG that is specified to actually looking into these things and seeing where can we standardize these things and where we're lacking. And hopefully with that kind of dedication of resources, the gap kind of shortens a bit.
Yeah, thank you.
Question at the back.
Hello. How do you envision enticing more hardware vendors to support SYCL? Because, for example, for PyTorch, users care only if it's PyTorch, and then NVIDIA comes and contributes really well-tuned CUDA kernels for their hardware, and SYCL is, as we've seen, 20, 30 times slower, and users, they can use PyTorch on NVIDIA, they will use PyTorch on NVIDIA. So perhaps if SYCL wants really its own spot under the sun, it wants some interest for more, buy-in for more hardware vendors. How do you see getting them on board?
If I knew, what we've been trying to do is do everything we can to be as open, as standard as possible, conformance tests, things like that. That we can make people come to SYCL. What we have seen is that people voluntarily come to SYCL because they look at it and go, oh, this seems to work for me. I made that determination about 7 years ago from OpenMP to SYCL because I kind of knew OpenMP wasn't going to work for C++. It's great for Fortran, it's great for C, and always will be. But for C++, so I started looking around and thought, SYCL is pretty close to what I think could work because it's basically C++. Even the library call is masquerading. Sorry, it looks like a library call, but it's not really a library call. But it is a library call. Maybe I'm trying to get to the deeper part of your question is how to get SYCL to be a major machine learning framework. Right now, a lot of machine learning hardware providers like to do their own. Like TensorTorrents, they have their own. CUDA has their own, but CUDA, NVIDIA, I guess. There seems to be a reluctance in the industry for some sort of standardized programming framework for machine learning. And this is normal. People like to roll their own for a while until they figured, because it's a competitive advantage thing, until they figured that there's no more point. And usually that's when people come together for a standardized framework. I know we have tried to sell SYCL to a lot of these AI-specific vendors, GraphCore and all that, largely unsuccessful because they kind of always said, we think our own stuff works way better. There's no need for using, even if your thing is standard, we don't think it's gonna. So we have to do a lot of work convincing them that the functionality is there, like you said, and the performance is going to be there when you do come over. That's kind of the barrier to entry, I think, at this point. Let me remind you that this has happened before too, with almost every programming language. They started out as some private language, and then eventually people unified to come together as a standard. So in my view, having seen this over and over again, it's not particularly new. We just have to struggle through this difficult times.
I'm not sure I have a brilliant answer. I mean, Michael captured it really, but it's funny because from a user perspective, the advantage of the open standard is you're not tied in. And the advantage of CUDA, presumably to NVIDIA, is that you know they've tied people in. So I guess it's as the market matures, as Michael says, and people realize that they're not going to become dominant. That then people start to settle on a standard. But I mean, I think it's a chicken and it's the old chicken and egg, right? If once you're seen as the only real competitor to CUDA for SYCL, then you become the natural choice. But I don't know.
Yeah, okay. I think kind of a follow-on question to that is, and it's kind of based on your comment earlier about, Chris, about the level of abstraction in SYCL versus OpenCL. And really the question is, has the machine learning community already standardized, right, on an abstraction? And the abstraction that they've standardized on is PyTorch or TensorFlow or essentially a DSL, right? If that's their standardized lingua franca, then where does that leave the lower level programming models like OpenCL and SYCL? And to play devil's advocate, is that search in vain to kind of standardize beneath the abstraction that's been standardized on, which is much higher? What's my answer to that question? Hey, this is my job, is to pose the questions.
You want to switch jobs?
I guess I'll shorten the question, right? Let's pose an assumption that the abstraction in the machine learning community that's standardized is at the level of TensorFlow and PyTorch, not beneath that. So where does that leave the efforts in standardizing beneath that layer of abstraction?
I guess if it's the case, and I don't know that you know the people can write code in PyTorch, whatever those very high level things are, and then get the efficiency at the lower level, right? If that's possible, and I don't think it is today, my belief is that it isn't today, but if that was possible, then it's probably game over, right? I mean, you've got very high, lovely, easy to write stuff, and you can get 100% efficiency, you know, because basically you want the highest abstraction with 100, right? And it's always a trade-off, yeah? And to be honest, in most computing, we do we all run Python. I mean, I've seen it. People write these Python scripts, and then nobody's actually aware this thing runs on one core in their 58-core Xeon, right? And they just don't care because it runs, right? And that's kind of the space we got to. But at the moment where we're chasing definitely efficiency, and that's what it's about, then you know it's that trade-off. And I don't know where that trade-off is, and it's probably different for different people. Certainly, I think for us and HPC, you have to get close to 100% because you know power and they have gigawatts of terabyte watts of power, but right. So therefore, it's too high. But it's a trade-off for different people, I guess, and certainly in lots of stuff we're doing, it's too high, so something lower. But I think SYCL is too low. I've been listening today. It's just, you know, it's too low. So somewhere, many ways in between, there'll be different abstractions. But the higher up you can go and keep your performance, the better.
Yeah, I think, like I said, it is a trade-off. But at the same time, there are standards out there for different machine learning operators, like the ONNX framework that defines what an operator should be like and how it should interact and stuff like that. Also, TensorFlow has its own way of doing that as well. I think there's been work with MLIR specifically from TensorFlow to try to push these kind kind of standardizations down to like a higher level where you have in the intermediate representation an operator that does look like convolution. This can add a lot of benefits, but it also can add a lot of cons. Stuff like you won't have one convolution for every situation. There are many different convolution algorithms that you can apply to different situations, and then once you get into the point of starting to standardize these things for, like, let's say you want to standardize a SYCL convolution, how are you going to get that standard well enough that it allows people to come up with new ways of doing it and new ways of these algorithms, while at the same time keeping the standard strict and making sure everybody's compliant to it? And is that very necessary for us? You know, it feels more of like a implementation-specific situation as opposed to what belongs in a standard. And so we can have these standards from like the top and like from the bottom, but we don't necessarily need to standardize every layer of it and allow kind of that creativity that then leads to these good results. You know, it's the reason that because we leave it to the users to figure out and leave it to the implementers to figure out these things, that we get interesting metrics of performance as opposed to this keeping everything in the standard.
So the question you asked is actually I really like this. You're saying, what role does SYCL or OpenCL, these kind of languages have, you know, in place of these higher levels of DSL? So if I go back to the original issues of why we have this separation, I would say the whole tension is because of the computational opportunities of DNNs and the practical difficulties from GPU programming, okay? And because of that, we have the industry and the academics have created these new systems like MLIR, like Tiramisu. Some of these are scheduling ones, some of these are polyhedral ones. Halide and TVM, definitely scheduling languages, to try to transcend this. But the problem we now know, so they were really hard for quite a while, but the problem we now know is they still remain less flexible in that the algorithm that they generate is still less efficient, less performant than the ones that are generated from hand-coded kernels from cuDNN, cuBLAST, and TensorRT. And that's why we still need that's why we still need, I think, things like OpenCL and SYCL to build the low-level cuDNN, you know, SYCL and therefore SYCL DNN. That's why those exist, because they can still outperform for the large part these higher-level DSLs like TVMs and Halide. That's why we still need to be here. Now maybe that's why the academics are working really hard to try to figure out this way of not having to go through the OpenCL SYCL layer.
I'm not sure what I'm saying here, but it's interesting that we keep coming back to GPU. I mean, we've got to be careful. We talk about GPUs. If we're looking at kind of problem down, that we don't say the solution's a GPU, now what's the problem, right? I mean, if heterogeneous computing, as it does, I mean, I think it's just cyclic, right? I think what happens is you get very, very specific accelerators, compute units, and then they become so widely used that they end up being plugged into they become part of, you know, x86 or something as they become very general. And I guess we'll just keep going around in circles. But, you know, as you said, GPU is something we had, right? I mean, it was graphics and it was there, and now we're applying something to it. And I think, as you said, FPGA will, it may well, I'm not sure I'm going now, but it may split, right? We mustn't just focus on the fact that we have to make everything work on a GPU, because and there's so much focus on GPUs, but actually there's a lot of people doing stuff which probably will be in greater numbers eventually, which aren't GPUs, right? Where there's accelerators which are not GPUs making use of machine learning in a way rather than doing machine learning, if you separate the application from the learning part.
I think there was a question at the front, yeah. At the front, yeah.
I was just going to add to your question. So I think it's more and more common nowadays to have, say, dedicated matmul cores like tensor cores and so on. And I think SYCL is potentially in a unique place in that it can offer a unified API to program all of these kinds of tensor cores, these matmul cores. And there are AI chip makers who are now considering that, especially with the joint matrix API, the extension to DPC++. We're kind of talking with some chip makers who want this. Yeah, just to add.
Was there a question? Yeah.
It's more a comment on the previous discussion, is that I think that CUDA or SYCL are just little implementation details that will disappear in AI. Because if you look at PyTorch, you have inductor generating some code at the end through, as Michael said, OpenAI, Triton. And if you look at what's really happening, so this OpenAI Triton was basically for ChatGPT, a master thesis, and now AMD is upstreaming their own ROCm version into OpenAI Triton, okay? But at the same time, Intel is upstreaming the SYCL version into OpenAI Triton, which means that by side effect, any other vendor supporting SYCL will just, and SPIR-V will just be able to leverage this effort to have PyTorch 2 working just on their accelerators. Of course, it might be suboptimal, but at least it's a starting point. So that's how I can see, just by serendipity, if you support SYCL, you will support by side effect PyTorch 2.
That's fantastic story. I love that. I mean, I try to get Facebook to convert PyTorch to SYCL for years, and they keep switching teams. Yeah. So yeah, they kept switching teams, and eventually I had to give up.
Okay, with many of our panelists actually implementing machine learning in libraries, as you introduced yourselves, things like OpenCL and SYCL, if you kind of go a million miles high, they describe things about the platform, selecting devices and that sort of thing. It describes memory here or there between the CPU and the device. And it also allows you to express different types of parallelism, so either kernel-based or hierarchical, simple parallel for that sort of thing. As you're implementing the libraries, what parallel or memory or machine abstractions do you wish SYCL or OpenCL had to make your lives easier?
I want block iteration space. It's still thread-based, and that's where it's actually not computationally efficient. I want something that is more tile-based, block iteration space iterations. And I think that if we can achieve that, we can definitely achieve something significant.
I do kind of have an answer, but it might not be quite the question. It's that it has to be invisible. It mustn't be. I'll be honest, I was interviewing not long ago, a few years ago, when I was still within Intel, and one of the questions came up. It was supporting GPUs, actually. And it was about, I can't remember the term they used, it was about, blah, blah, blah. And I said, what are you talking about? Is that multi-threading? Yeah. And it was like 20 years after, the first multi-core processors, you still can't get, like, serious developers that we're supporting directly. The biggest problem is to get them to thread their code, because it's just so difficult for most people to do. So however you do it, you have to do it in a way that people don't have to think about it, because as I say again, we're talking about mainstreaming this stuff, and most people just don't get their head around it. However much you try and explain it, it's, it just becomes too complex a problem. So I'm not sure what I want, but what you don't want is, you need to hide those concepts. You need to somehow get the, you know, it just needs to be some auto-magic type thing that you know, and when we try and do it in OpenCL, right, we try and do it with the, but then it you know, the code then becomes quite difficult to read, and people get lost, and in actual fact within ours, I don't think we're actually got a problem there within, you know, we don't have any, but that's the thing, is facilitating tools where it just happens and people aren't aware of it, because most mortals can't deal with that stuff. This is not representative, this group of people of the world. That's the problem. It's the geeks here, right? And we want normal people to be doing this stuff.
For me, it's a more specific feature that I'm missing, but I think the general idea could be expanded to other features. Like we currently have an implementation laying around which uses tensor cores in CUDA, and we want to implement it in SYCL, for example. And as you said, joint metrics is an extension in DPC++. And you said beforehand that you don't think we have to add an extension to the SYCL standard using, for example, the joint metrics. However, I think it would be a nice idea to add an optional extension, because for an implementer that uses, then, for example, joint metrics, I can say, okay, I use joint metrics. If DPC++ implements it, it's okay. If, for example, IWOCL decides in 6 months they want to support CUDA tensor cores also, then if we have a standardized API, I can say, okay, I've implemented my kernel using this API, and I can plug in IWOCL and it just works. And if these extensions are always vendor specific, I have to change my code to use the IWOCL API, which will be different if it's a vendor specific extension than DPC++. So it's again burden for the maintainers and developers.
Yeah, I was going to comment on that as well. It's mainly missing the API to interact with the dedicated hardware. Like it's going to be just kind of impossible for me to beat CUDA if they have a dedicated convolution, dedicated hardware dedicated to convolutions. There's just nothing I can do about that. So until we have an actual API to interact with those pieces of hardware, we're always gonna lose to that.
Okay. And with that, I think we've reached lunchtime. We'll thank our panelists again. Thank you.